All right, I'm now going to talk about the moon's altitude and azimuth position. This gets complicated, and let me show you why. So here's our celestial sphere again, way back to our celestial sphere. Here's the celestial equator going around. So this is the north celestial pole, south celestial pole, celestial equator. But then we had the path of the sun going around like that. This is the ecliptic. Now what makes the moon challenging is it doesn't match the ecliptic or the celestial equator. It has another tilt. It goes like this. So the moon's orbit is tilted from the ecliptic, and this angle here, or the angle of tilt, is actually currently 5 degrees 9 minutes, or 5.14 degrees. We're just going to round that to 5 degrees, so it's pretty much exactly 5 degrees off from the ecliptic, but remember the ecliptic is the path of the sun. Okay? And there are 2 points where it crosses. These points right here where it crosses, where the moon's orbit crosses the ecliptic, those are called the nodes. There's 2 nodes. There's a node there and a node there. Let's call it a node. One's called the ascending node, one's the descending node, as it's going positive, and then when it's going negative, remember it's moving in this direction here. And this is the reason why we don't have eclipses every time we have a new moon or a full moon, is because most of the time the moon is above or below the sun in the sky, and so it doesn't cross exactly across where the sun is in the sky. And because of that, we don't have eclipse. Remember, this is 5 degrees difference here, but the moon and the sun are only a half a degree across in the sky. But if we have a full moon or new moon, when the moon is near one of its nodes where it's crossing, that's when we'll have eclipses. That's why you only have eclipses a couple of times a year when it happens to be at those right positions, what we call the eclipse season. Now, we're not going to talk a lot about eclipses in here, but what we want to do is figure out where the moon's position is, or how this affects where the moon is compared to the sun. The other challenge with this is because of this, so I can draw a line through the center here, through the center of the nodes. It goes from one side to the other right there. Well, this orbit of the moon that has a 5 degree tilt, that whole orbit wanders around, or we can call it a precession. So the orbital precession of the moon makes the whole thing, so if it's like tilted like that, the whole thing goes around like a plate that's like spinning around. But it takes 18.5996 years for this to go around once, or 18.6 years. So what does all that mean? What that means is, if we assume this is a horizon here, and we're looking out to the west, and we see the moon set, the moon will set at an extreme position. So if the sun, the maximum sunset position is here. So this would be sunset on the winter solstice. And then this would be up here, would be like sunset on the summer solstice. So we're watching the sun set. Well, the moon, remember, has 5 degrees more extreme than the sun does. So the moon can go all the way out to here, 5 degrees further. So this would be the moon's southern extreme setting position. And then it would get up here, would be 5 degrees above this, and this would be the moon's northern extreme setting position. But because of this 18.6 year period, what's really going to happen is you will see it set here, and if you go out on the same night the next year, it won't set in the same position, it'll set further over. and I'm not even close to being the right side, but it'll set further over. So every year, I should have 9 of these. So every year it's going to set in a different position at that same day of the year. So if I went like out on the summer solstice and watched the moon, where the moon was going to set that night, it would set at one position and then it would go all the way across. It would take 9 years, half of this cycle here, to go all the way to the other extreme, and then it would take 9 years to go all the way back again. So you'd have to watch the moon for a really long time to understand how all this changes occurs. We don't see a lot of that occurring in archaeoastronomy, except there is an intriguing thing. Remember on Fajada Butte, there's the spiral. Well, it just so happens that on Fajada Butte, this spiral has exactly 9 spirals. So when the full moon comes, it'll be there. The next year, it'll hit that spiral. The next year, it'll hit that one, and so on, taking 9 years till it reaches the extreme, and then it'll go back again. So over 9 years going one way, the moon will keep rising further and further out, or the shadow will go further and further out, and then the shadow will come all the way back. Now, obviously, that's not proof that they understood this cycle of the moon, but it is intriguing that they had their spiral be exactly 9 turns from the outside to the inside. Okay, so what we want to do now is figure out how we're going to calculate those things. So the first thing we're going to do is we're going to look at the moon's altitude. And if you remember, with altitude problems, we always do a Herb diagram. And so with the Herb diagram, I don't have my protractor here, but you should be using a protractor. Let's see how good I can draw it freehand. North, south, Herb's in the middle. Altitude, we want to figure out how high it is on the meridian. Okay? So let's do it from latitude 33 degrees north. We want to figure out the maximum and minimum moon altitude. From this position. We do it the same way we've done the other ones, where we make our north celestial pole here so that it is 33 degrees high. This is north celestial pole. And then from there we go over 90 degrees to the celestial equator. And then we subtract those two from 180, we get that this is 57 degrees high. Now the difference with the moon, if we don't have the moon's declination, remember we always would then put the declination of either the sun or a star from the celestial equator, because that's where declination is measured from. When we say maximum and minimum moon altitude, that's always from the sun. So we say from the sun, the maximum the moon can be would be the sun's altitude maximum, which is plus 23.5. And if you add 5 degrees more, it's 28.5 degrees. So the maximum declination of the moon is 28.5 degrees. Maximum north declination. The maximum south declination would be negative 23.5 minus 5 degrees, which is negative 28.5 degrees. So to figure out the maximum and minimum altitudes for the moon from a specific location, in this case Commerce, Texas, we just go to the celestial equator and we go up 28.5 degrees for the maximum. This is the maximum moon altitude. And then to figure that the altitude, remember, is this whole thing, it would be 57 plus 28.5, which gives me 85.5 degrees. That's the maximum moon altitude. For the minimum, we would take 57 minus 28.5 degrees. And when we do that, we get 28.5 degrees. And so that would be right here. This is 28.5 degrees below it, and this is the moon minimum altitude. Now, if you wanted the altitude of the moon on a very specific day of the year, you'd have to go look up the sun's declination in the sky watchers for that day, and then add 5 degrees or subtract 5 degrees, depending on whether you want the northern extreme would be adding, the southern extreme would be subtracting 5 degrees from the declination of the sun. So remember, the moon's position is always, the extremes are always adding 5 or subtracting 5 from the sun's declination. We don't have the moon's declination directly. All right, so that's how you find the moon's altitude. All right, next video, we're going to work on the azimuth or rising position.